Hey, hi viewers. In this video, I will be explaining about why the trusted algorithm is being used and is beneficial in case of confidential transactions. And this, I'm not saying it. This is coming up from a paper that was published from the Shandong University, and I will be going through that. So I hope you remember about this workflow diagram between the Alice and Bob in the previous videos, where I've been saying about the privacy and how it can be preserved using the encryptions, different encryptions, and the different ZK proofs that can be generated. And also you see that I hope you remember about the difference between the auditor and supervisor, where the auditor, with the by preserving the privacy of users, he will be, or that particular entity will be able to audit the transactions. And the supervisor, in case where without the permission itself, they will be able to monitor the transactions and verify the proofs. So that's a basic difference. But anyways, I will go through the paper and then we can look into it. So if you want to read more details about this paper, you can just go to this ePrint and you will get that with the 319 in the 2019 year it was published, and you will also get the source code of this in the GitHub. So basically the thing is, the private in the private systems, you Alice and Bob will be able to transact it, but the other people, like in Ethereum and Bitcoin, the public viewers will not be able to see the transactions, but in Bitcoin and Ethereum you are able to see those things. So how you can make it private? This is the paper that's been describing that, how the sender and only the sender and recipient will be able to know what was transferred. Now the thing is, of course, in the confidential transactions, when the transactions are transferred in the form of encrypted format, and also the proofs are being published there, so the auditor will be able to run the function, and the function means that it will be something like a company policies, where whether the users who are participating in these transactions are compliant to this particular company policy or not. So that's been checked here, and this will be applicable for all the transactions that's been happening for a period of for a particular instance. This particular function is being checked. In the centralized payment systems, you know that the Visa, GPay, and any of the things where the ledgers are maintained in a central format, and the privacy is something like it's not for the users, it's been protected by the centralized system actually. So the centralized authorities, they will be able to get a full control of it in case of centralized payment system, but it's not the case of decentralized, where only the users will be able to handle those assets. And in this paper, the confidentiality is being established with the help of auditability, means that the anonymity is being right now avoided. Because of that, the auditor and the supervisor roles play a bigger thing here. I mean, they are able to audit it, and also they are able to supervise it. So the anonymity is something which is slightly denied in this. Now, this is the workflow where you have the public parameters that's been set up. And next one is about the creating the accounts using the public parameters, and then of creating a transaction. That means that transferring the coins or dollars from one account to the another account. And also after that, the justify, verify, and the audit transactions are also happening. So we will get into detail. So this paper is basically covered of verifiability. Whatever the transactions that happens in the ledger has to be verified. Authenticity has to be there. Confidentiality has to be there. That means that there should not be a third person that should know this transaction, and it should not. It should be sound. It should have a soundness property, which means that there should not be an illegal transaction that should be passed from the sender to the recipient, or the parties should not be doing any illegal things. Auditability is the auditor or the external entity that will be able to do the, that will be able to, comply, and they are basically responsible for the compliance of company policies. So in the former security models, the oracles where you trust an external source there, and that means that almost all the actors that's passing the parameters into the oracle are honest accounts or the honest users. But if you have a corrupted accounts, then you will be able to inject an what you say a corrupted transaction, and based on that, the whole thing of the security model will fail here. So that's the thing, when you depend on the oracles, many of the hacks happen, and that can be prevented using this cryptographic proofs with the help of the non-trusted way of verifying the proofs, or the trustless way of doing the things. So here the thing is that yes, it follows the additively homomorphic encryption properties, and the signature and the ISC, the encryption and the signatures are clubbed in with the help of reusing of the keys here. So that the thing is that, of course, the signatures, when it's been done, you need to verify it, you need to generate the proofs, and that's been done using the NIZK with the help of the bullet proofs, and also the range of numbers that's been passed on, that also needs to be checked, and that's also happening in the NIZK. So NIZK is a non-interactive zero knowledge where you are not directly interacting with any verifier, you are just generating the proofs. And here, of course, with the key separations, the key reuse is the thing that this paper is using it. So it will be something like the same key will be reused for the signature and also for the encryptions. So that means that ISC is something like integrated signature and encryption, where the key reuse is happening with the primary public key and the secret key. And this will enhance the efficiency of the system. So of course, this is the building blocks, where in the ISC, that is the integrated signature and encryptions, you are having a setup for public parameters, then the key generation, sign, verification, and encryption decryptions happen. And the NIZK needs to have a soundness and a ZK property here, and also you need a CRS generation here for any zero knowledge, but it is not going to use any third-party setup because the bulletproofs are being used for that. Now the thing is about the setup. The steps to do this thing. One is the generating the setups. During the setup, actually the public parameters are generated, and using the public parameters, using the public parameters, the accounts are being created here. So the thing is that public key and secret keys are generated using the public parameter, and then you create an you create a commitment using the encryption function. And the encryption function, for that you need to pass the message, random number, and also the public key, which will encrypt it. And for revealing the balance, you need to use the same, the revealing the balance of an account. Let's say if the account is encrypted, if the account transactions are encrypted, the account holder should have a commitment and also the secret key to his account, and only then he will be able to see the balance of his account. So it's purely protected there. So with the help of cryptographic mechanisms on the algorithms, this you will be able to hide the balance of your account from the public UA. Next one is about the creating the transactions. The transactions are getting created here, where you are transferring some amount of coins from one sender to the recipient, and for that the two commitments are created, and the commitments are being passed in the form of memo. And then you run a you run a proof generation mechanism with the help of witnesses with this particular number of coins and all the secret keys and random numbers. The proofs are created, and then you have a intersection of the different other logics like the equivalent, right, and solvent things, and based on that the memo is the memos are created, and then based on all these proofs, actually the sigma proof, which is the final proof, where this will be generated based on the signing of the user. And remember, the key pairs are being reused here, for which was used for the encryption. The same thing will be reused here. And yes, based on this, the output transaction is generated. Then once the transactions got generated and it's been transferred, then you verify it The verification will be done based on this data structure here. You have a serial number, you have a memo, you have different proofs, and the final sigma proof that was generated in the last step. And based on this data, the verification happens here using the NIZK. And after the verification is successful, the commitments are being updated. That means that when the sender passes an 100 coin from one account to the another account, that is to the recipient account, the sender account will be getting detected, and the receiver's account will be getting added. So this is all the encrypted data that's getting subtracted and added because of the additive homomorphic properties that's been followed. And then you have the justifying the transactions. That means that for a user, when it runs the proof, it needs to prove that it is following the company policies. That is for the it is preventing the anti-money laundering policies, and also in case of tax payments, the following policies have to be followed. That means that out of V coins, X amount of coins has to go in the form of taxes. So this type of company policies will be written, and that will be verified by the auditor here. So for that also they are using the NIZK. So the thing is that yes, these all things are happening, and as you remember, in the ISE we are using the public key encryption, and that is the LGML, the standard LGML thing. But in the standard LGML we have a trapdoor here, that is the oblivious thing, because of that oblivious thing, it's not directly compatible with the ZK, that is the bulletproofs here. And for that we need to do a lot of bridging for that to happen, and that is a time consuming process. So instead of that, a twisted LGML is being invented, which will directly have the Peterson commitment thing integrated, and will not have an oblivious trapdoor. So that will be removed, and based on that the twisted LGML is being used, and that's going to give a smart transfer actually. So that will decrease the transfer time and also the gas cost. So here there are different comparisons that's been done with the standard LGML and the twisted LGML, and also with the Pallier. And as you see, only the public parameter time is slightly negative, but the other things are almost similar. But the size and efficiency, in case in that comparison, you can see that when it's being clubbed with the bulletproofs, it's really efficient, as the standard LGML is much more complex. The same thing with the Pallier and LGML, where the twisted LGML is being a winner in this. So this is how it's been used, and for the setup and key generations, actually the Schnorr signatures are being used because it's identical to the twisted LGML. So that's why the ISE integration works perfectly. But the only problem is that the auditability works right now, but there is no supervision that's happening. That according to this paper, it's in progress actually. So this is how it is, how the confidential transactions work, and based on the ZK ledger and Zeta, this paper PGC, it is much more satisfactory and much more good. But the anonymity is not being implemented in this paper. But the confidentiality, it works perfectly, and also the performance is very good, and also the auditability. So thank you for watching.